In this lecture, we're going to work out problems based on the differentiation rules. So we're not going to be using the definition of the derivative, but the definition of the derivative is embedded in these rules. On the left here, what we have is the general rules, and we're going to be focusing right now on the constant rule, sum and difference rule, the product rule. And these rules on the right involve specific functions. So this is x to a power. Notice it's just x to a power. The variable is x as specified in the operator. Derivative of sine is cosine, and derivative of cosine minus sine. So these are specific functions, and this is for just general functions. We'll come back to well, I guess we're going to use the quotient rule as well here, right? All right, okay, well, let's begin with a specific problem. And again, we're going to start with basic problems and develop a technique and work to more and more complex problems as we go. So here the function I'm specifying is 1 over x to the fifth, and we want to determine the slope of the tangent line at the point specified when x equals 1. Right, so again, change in y over change in x when x equals 1, and we get the y value from evaluating the function. Okay, so the first thing we want to do is we want to put the function, well, we want to notice that this function is actually differentiable everywhere except 0, right? It's a rational function. So we can use the differential operator to evaluate, to find the function fx, and then use fx evaluated at x equals 1 to find the slope of the tangent line, right? So, okay, I want to put the function in the correct form. So again, I don't have a differential. Well, I guess I could use the quotient rule, but I don't. This is really not in the form I'd like it to be. I want to use one of the prototype forms. Notice again, a over b, b not b equal to 0 means it's undefined, means that x cannot be 0. Again, train yourself to think in a fixed manner. Now, what I'd really like is to raise it as x to a power. That's what we're looking for. I have a rule that works for x to the power. And again, you can get out your crib sheet or look at the rules on the beginning of the lecture. These are the rules we're going to use, and it has to be one of those rules. At this step, we're just doing algebra to set everything up in the correct form to make the calculus easier. So again, I have a rule x to the power. Again, I could use the quotient rule 1 over x, but that's just not the way to go about this. I mean, this is a much more straightforward process, x to the power. I'm looking for x to the power, sine, cosine. Later on, we're going to add e to the x and log x to the family. And again, you can add you look in the back of your book, you have other simple forms, but there's still just a finite number of basic forms you can do. So x to the power being one of the most common. So now I'm going to determine the function fx, the derivative, the function that's derived from f through the differential operator. So once again, this is a template. You can come up with your own template, but it's still going to have, it should still be a fixed form, an algorithm. So the function f goes in, I apply the differential operator, and the function fx comes out. So again, you're going to see fairly standard. You don't need to reinvent the wheel. You don't have to do it my way, but you should have a fixed way that doesn't change with every single problem. Now, at this point, and again, in the next problems, I'll let you guys work it out, or I hope you work it out. I'm going to simply replace, so again, this is definition, and I'm going to replace the function, well, by its definition. Right? Notice every step is a definition. It's not mystic experience, not because I said so or somebody else says so. It's all defined. I'm simply going to replace the rule fx by its specific rule. Right? I substitute the specific rule for the function. And now what I need to do is all the preliminaries are done. Find one of the rules. So if you look at your crib sheet, what's the only rule that can apply? And that rule is simply going to be the power rule. Now again, I don't necessarily suggest you write this down, but in your mind you should be aware I'm using the power rule when I'm applying the power rule when r equals minus 5. So it's really just a plug and chug experience. There's no thought in this. There's no being clever. There's nothing really going on here. I'm just applying the power rule straightforward. And now just do some simplification. That's all, just algebra at this step. And again, how you want to write it with the algebraic simplification is, well, it depends, right? So it's good to practice and so forth. So there I have it. I have the function fx fully specified. Notice I'm specifying the whole function fx. I don't really need it for this example. I just need to evaluate fx when x is 1. But again, it's a good habit to get into to define the domain, define the whole function, because if you're going to take the second derivative, which we're going to look at in the next series of lectures, higher order derivatives, it's good to have it all specified for subsequent action. So again, it's just good technique. Okay, I'm just re-summarizing the function. Again, on a test, I wouldn't take the time to do this, but again, it's just good technique. Now, if I want to determine the slope of the tangent line, once again, it's just a definition, right? By definition, dy dx evaluated at the point where x equals 1 is this function, the derivative fx, evaluated at x equals 1. It's as straightforward as that. And so minus 5 over, well, you substitute 1 to the 6th power minus 5. And there are derivative calculators on the web. You can just Google derivative calculator, and this stuff is there. But like, again, I emphasize, like when you first learned how to add, subtract, multiply, and divide, you do it by using a calculator now. But you still should know how to add, subtract, multiply, and divide. It's the same with using derivative calculators and integral calculators and even Taylor series calculators on the web. You should know how it works, and really that's what we're really pushing here, understanding the basics. So I have the slope of the tangent line. And again, I derived it not from the definition this time. I derived it from evaluating the function fx, the function derived from f. Now, of course, the definition of the derivative is embedded in the rules, but okay, we're not directly working at that low level, assembly level. Okay, and then of course the question is like it always is, find the slope, determine the equation of the tangent line, and we've done a lot of these. Again, you can pause and try this. This should not take more than 30 seconds, right? Be quick and efficient about this. Okay, let me jump in. I'm just specifying my function again just to clean things up. I list my data. Right? When I specify x equals 1, because it's a function, I know there's an xy pair. Right? So I have the point, and I have the slope from the previous example. A line is y equals mx plus b, and again, we just simply substitute in the slope, substitute in the data, the point, and solve for b. Y equals mx plus b is done. And then again, the real question is find the linear approximation. And again, pause it and just write it out. It should take 30 seconds, done. Well, if the tangent line looks like this, the linear approximation looks like that, and we're done. And here's just a graph. Again, you can see the linear approximation is a good approximation for the function in a neighborhood, right, of this point. If you want more accuracy, you take a smaller neighborhood. And so, I mean, that's what we're really looking for, the linear approximation. Okay, let's look at another problem. So again, I'll pause it here and try to work through the exact same steps, okay? So in your preliminary step, do the algebra. Put the function in the correct form. You're essentially looking for x to power sine, cosine at this point, that's all. So a constant times that, plus or minus constant times x to the power, plus or minus constant times that kind of form. So do that in a preliminary step. Set the problem up correctly. Then when you apply the differentiation rules, you really don't have a choice in the order in which you use them, or at least not usually and not much. But give it a try. Get comfortable with how the process works. Learn to play the game. Learn to use your tools efficiently. Okay, give it a shot. Okay, let me jump in. I notice that the function is differentiable everywhere but 0, we'll see, in the domain. And so we can use the differential operator. Notice in order to use a differential operator, I have to be differentiable on an interval, right? So what does this preclude? Piecewise functions at the point where the definition changes. So that's why this is a good step to look into. Again, problems aren't gimmicks or tricks. What happens is you're not prepared for it. So I need the function to be differentiable on an interval around x equals 1, and you can see that that's the case here. Okay, so I can use the differentiation rules. Now, here's my function, and it's not, again, in the form that I'd like it to be. 1 over x squared is not, ideally, it's not set up right. Again, we could argue, but what I'd really like to write it 1 over x squared is x to the minus 2. So notice what I have. I have a constant times x to a power plus a constant, okay, 1 times x to a power. And again, I'm looking for plus signs, plus cosine, that kind of stuff out here. But this is the form I want. This is going to make the differentiation easy. And it's purely an algebraic step. It's not a calculus step. So my thought is do the algebra, do the preliminaries first before you get to the calculus. All right? And notice, again, it's different forms do different things. If I write it in the form of a rational function, a rational expression, I have polynomial or polynomial. I have a over b. B not equal to 0 means it's undefined. X equals 0. Now you can say it is true here, but you have to worry about algebra functions here. When you write it as a over b, I guarantee that this expression is undefined when b is 0. So this is where this comes from. So again, different forms tell you different things. Again, it's not right or wrong, better or worse. They're pro and con. Certain forms are better for certain functions, determinations, certain better others. For calculus, for the derivative rules, we just want to middle this expression here. So we're going to determine the derivative, the function fx. So once again, notice this is just the definition. The function f goes in, I apply the operator, differential operator, d dx, to that function f. And what results, the output is the function fx. So fx, again, is derived from the function f through the differential operator. So that's just a definition. And now I'm just going to substitute it. And again, you should see these steps as inevitable. You have no flexibility here. And when you work out the homework problems or any problems, you should be quick and efficient with this. This is not a lot of thinking. F of x is, we're just going to substitute in the rule. Right? This is the definition of the rule for this function. I just plugged it in. Now again, when you look at this expression, you have only one possible choice of the differentiation rules that you can use, right? One possible choice. So again, if you haven't done it, pause and try. Look at the crib sheet or the notes at the very beginning, and you'll see that I only have the difference, the difference rule. I mean the sum rule. I'm sorry, the sum rule. And again, I don't have to write it out explicitly, but you can see my function, my first function is 4x to the cube plus, and my second function is x to the minus 2. And you just literally plug and chug it and you arrive at this expression. Now, we've broken one problem into two, and you're free to look at either one. Again, this is maybe where you have a choice, but looking at the first one, there's only one possible rule you can apply, right? Just by the process of elimination, look through the rules, and you'll see that it's the constant rule, right? So my constant here is 4. I literally just plug it in. Again, there's no thought involved. You're just literally plugging and chugging at this point. This is not, calculus at its noblest or its greatest. Again, this is the kind of stuff you should do with a derivative calculator and if you need it and not be putting the effort into it. It's just plug and chug. So now I'm looking at these two other expressions, and you can do either one, but what rule can you use? There's only one possibility, and that's the power rule. I don't like to usually do both at the same time, but this is pretty straightforward, and again, it's fine to shortcut it a little bit. So in the case here, the power is 3, and in the case on the right, the power is minus 2. So then you literally just plug into the rule, and now you do the algebra and clean it up. And again, how you want to write it is your business. I mean, you can write x to the minus 3 is 1 over x cubed, that's fine. Okay? And again, the obvious questions, again, I can continue to simplify whatever form I prefer for whatever, but when I write it as a over b, b equals 0 means the function is undefined, so that's x equals 0. Okay, and then we can proceed. What is the slope of the tangent line? So I'm just repeating the function in the slide, new slide. So the slope of the tangent line. And again, if you haven't done it, pause the video and give it a shot. I'd really like you to get the hang of it as we work through these problems. Okay, so again, by definition, we constructed this function fx by literally making it at x equals 1 the slope of the tangent line of the function f when x equals 1 at the point x equals 1 and the y value associated that with the function. I mean, this is the definition. This is how this function fx was constructed. And now we just have to evaluate this rule at that point, and it's just purely an algebraic expression. And it equals 10. So the slope of the tangent line at the point associated with x equals 1 is 10. It's as straightforward as that. Okay, and again, you could go ahead and calculate the tangent line in a linear approximation, but we're concentrating on the differentiation rules right now, so I'm going to go with that. Now here's another good example. Again, why don't you pause the video and jump in and give this a try and see how you do. Again, try to put everything in the correct form and it will make your life a lot easier. Okay. Once more, I notice that this function is differentiable everywhere except 0. So I can use the differential operator anywhere that I'm not 0. And again, in this particular case, I'm not trying to determine the slope of the tangent line or even a function fx. I'm just trying to determine the rule associated with the derivative function. Right? So that's what this notation means. This is just the rule. So I'm not asking for the domain or anything. I'm just looking for the rule here. I'm not looking for the slope of the tangent line, just this rule. Okay? And again, I can use the differentiation operator. So here's my function again, and I know it's not defined at 0 because, again, a over b equals 0 means I'm undefined. Again, have a process of thinking. That's what I'm really trying to encourage again. All right, now let's look at this. Is this rule in the form that's suitable for the differentiation rules? Well, you could argue, yes, I could use the quotient rule, but that's really, you're working, too hard. Fight smarter, not harder. Let's just use the algebraic rules and break this down, and then we're going to simplify. And it's just this simple rule, right? I mean, x to the power, constant, plus or minus constant x to a power, plus or minus constant x to a power. This is going to be much easier to do the calculus on than the original rule using the quotient rule. Now, will you get the same answer? Yes. But again, the issue is, I feel, probabilistically, you're more likely to make a mistake doing the quotient rule in this more complicated expression than you are just doing the sum, difference rule, power, constant rules on this rather simple expression. I mean, you can pretty much do this in your head, right? So again, fight smarter, learn how the game is played, and then it shouldn't hopefully be that bad. Okay, if you haven't done it, set it up and derive the function fx using the differentiation rules. Again, you have no flexibility in how you want to proceed, or very little. Once again, I'm going to set it up in the same way. The function f goes in, I apply the differential operator, the function fx comes out. I'm going to substitute the particular rule I have here. Now, I just, I wouldn't suggest you write it as x to the first power and 3 is 3 times x to the 0 power. I'm just trying to emphasize at this point that we do have the differentiation rules, and that's how you should be thinking. I mean, in subsequent, later on in the semester, I'll drop all this, and I'll even drop the derivation. We'll just do it. So the rule I'm going to apply, and again, I should take 2 steps, but it's a sum and difference rule. So I have the first term minus the second term plus the third term. And again, you could break it down in a couple of steps, but I'm not against taking shortcuts where it's pretty straightforward. But there are rules associated with everything we do. It's not because somebody says so or a mystic experience, right? And now I'm going to take out the constant rule. Again, if you haven't worked these out, please try to work it out. You can do this stuff, and it's not a Herculean effort. You should be able to do it. So again, you really didn't have any choice what to do there. And now when you look at it, the 3 remaining terms that need to be evaluated, it has to be I'm just starting a new slide, just has to be the power rule. And again, I'm just applying the power rule with the power x equals 1, the power rule with x equals 0, the power 0, power rule with x equal to the minus 2. And it's just a matter of plugging and chugging and then evaluating the algebra and cleaning everything up. Okay, and again, how you choose to write it is your business, but I'm asking only for the rule associated with the derivative, right? The function derived from f. That's all I'm asking in this case, okay? So again, it was a fairly straightforward process once we did the algebra at the beginning, and you should see it as such. Okay, here's another one, and again, pause, try to do this, and don't go crazy. Do the basics. Try to follow the guidelines I'm suggesting, and I think you'll find it's a bit easier than maybe otherwise. Okay, give it a shot. Okay, once again, this is going to be differentiable everywhere. It's actually going to be a polynomial. It's differentiable everywhere. So I can use the differentiation operators, which are differentiable on intervals, right? So let's simplify. Now you could jump in and you could say, well, I've had calculus, so I'm going to use the product rule. Again, that's just working way too hard. Just distribute the x between the two. Again, combine the powers. This is all algebra, and you're in good shape. So I have x to the third power plus x to the first power. So one of the issues with the test is people say it's too hard if you don't have enough time. You don't have enough time because you're really making a mountain out of every problem that doesn't have to be, right? Here's a good example. You could use the product rule, but it's too much. Again, I just think it's much more likely to make an algebra mistake. This is pretty straightforward, and it's just algebraic. So now if you haven't determined the derivative yet, give it a shot. Again, the rules and the order of the rules you use, it's inevitable. You have no flexibility. So give it a shot. Once again, I'm going to start every problem exactly the same way. I'm going to substitute in the definition of the rule. And now if I look at this, what's my only choice? Again, when you look at the rules I gave at the beginning, or it's the first slide or the crib sheet I post, what choice do you have here? I mean, it has to be the sum rule, right? Again, it's inevitable. Learn to see these rules in the problems, and you'll be very efficient. I mean, somebody can maybe trick you with algebraic gimmicks, I don't know, but this is straightforward, right? And now when I look at these two terms, right, I break the one expression into two. When I look at these two terms, it's going to be the power rule, right? It's the only rule. On this term, x cubed, the power is 3. X to the first power, the power is 1. Plug in, and it's just an algebraic exercise. Okay? And so this is the rule, and that's all I asked for in the problem. Determine the rule for the derivative. Okay? Again, it's just a matter of speaking the language. Okay, here's another one. Again, you can see each time these problems are getting a little more involved. That's fine. Give it a shot. Again, pause the video. Make sure you jump in and try. We're just looking at more and more slightly involved problems. Don't be afraid. If you make a mistake, that's why we're doing this. Okay, again, it's differentiable in the interval. And again, I want to keep saying this. If you had something that was piecewise, at the point where the definition changes, you have to use the definition of the derivative, right? You don't have a choice. You have to use the definition of the derivative. That's really where that's actually still useful. You can't derivative calculator that or anything. You actually have to go back and apply the definition of the derivative. But for something that's defined on the interval, we're good to go. We can use the differentiation rules as long as we're not at 0. So again, here's my rule, but it's not in the form I want. Again, I want constant x to the power plus or minus constant sine plus or minus constant cosine. And that's not what I have here. So what I'm going to do is when I have the cube root of x, of course, it's x to the 1/3. And if it's in the denominator, I can bring it to the numerator as x to the minus 1/3. And again, I have all the rules, algebraic rules that I used in developing every example for this course listed on that crib sheet. Again, there's only like 20 of them. So if you're struggling with the algebra, practice it. You're not going to get stronger if you don't practice it. And you'll see it's usually the same main ones over and over again. So now this is again a constant times x to the power plus a constant times cosine. This is in the form I would really like it to be. right, in order to apply the differentiation rules. So this is purely algebraic step. I'm going to do it before I even get to the calculus. Again, why? What advantage is there to combine the algebra and the calculus? Okay, so what I'm emphasizing is it has a correct form, right? Constant times x to the power constant cosine. And again, in order to determine the domain, the easiest way is to write it as a over b. B equals 0 means it's undefined. And so this is where I get x not equal to 0. Okay, so again, the form all the way on the right here is useful for the domain and other things. The form here is the one I want to use for the differentiation rules. Okay, so determine, if you haven't yet, try determining the function rule for fx. Again, see that you do not have any choice. Just simply apply the differentiation rules, as I said, from the crib sheet of the first slide. Again, do it quickly, efficiently, and just be done. Okay, again, I always start out the same way. I apply the definition of the rule. And now I look at the particular problem, and I see I have one possibility. Again, look at the crib sheet. Only one rule applies, the sum rule. And I've broken this complicated problem down into two basic problems. You can start with the term on the left or the right. If I look at the term, well, either of them, I only have one possibility. I'm just rewriting the slide again because it's getting complicated, but I can take out the constant, right? In the first term, the constant is a 2. In the second term, the constant is a 3. And just applying the rule directly, that's the only possibility I have, the only possibility. Now, if I look at either of these terms, let's say the first term on the left here, I only have one rule that applies here, and that's the power rule, right? There is simply no choice. You should be able to do this quickly and efficiently. Don't waste time on these problems. Don't waste time. Get it done. Know what you're doing and drive on. The term on the right, again, one possible choice. The derivative of cosine is minus sine. And again, pay attention to the negative there. I mean, it's a sloppy mistake to make, but it's understandable. But again, pay attention. The derivative of cosine is minus sine. And now it's just a matter of cleaning it up. How you want to write it in the particular form you want to write it as. It's just your business. You might, again, check the answers in the back of the book to practice your algebra again. So that's the rule for the derivative, right? That's the rule for the derivative. And you could use that to find the slope of the tangent line and the tangent line in the linear approximation. All right. So these are all the problems that I've worked out. Now I'm suggesting try some homework problems, develop your own style and technique. Again, try to simplify the algebra first. Look for the keys, right? Constant times x to the power, constant plus or minus, constant times sine, constant times cosine. We'll add other functions to that list later. But that's what you're looking for, okay? So try to do the algebra first and then look at applying, again, and know where you're going with the algebra, and then apply the rules and be efficient about it. Don't take forever. You should be able to do a half dozen problems and feel comfortable with this, okay? Good luck with that.